Welcome everyone. Um, So today we want to uh, begin with some questions. Uh, we are going to uh, the problems uh, on kinetic theory of gases. So I have a list of questions. Let's begin. So the first question which we have is that of uh, XO2 molecules. So these XO2 molecules, we want to figure out what X is. We are given that this X can be option A sulfur, option B carbon, option D oxygen, option C oxygen, and option D. Okay. Question is at 327 degrees Celsius, the RMS speed of XO2 molecules is same as that of oxygen molecules at 27 degrees Celsius. From this information, we have to find out what is X. So we basically have to figure out okay what equation we have to use. So for RMS speed, we had two equations. One was square root pressure divided by density. Other was square root 3 RT by molar mass. So we are having temperature here. So we'll be putting the value of temperature in that equation and as also the value of molar mass as well. So we'll say square root 3 RT by m. This is the speed of oxygen molecules and speed of XO2 molecules is square root 3 RT divided by molar mass of XO2. Right. So the question which I have here is that what is the value of T which will substitute here? So we won't put the value of temperature T here as degree Celsius. Instead, we'll be using the value of kelvins. So we'll have to convert this degree Celsius value into kelvins. So we'll say square root 3 R into temperature of oxygen. So this would be 273 plus 27, that is 300 kelvins, divided by the molar mass of oxygen. So molar mass of oxygen is some 32. 16 is the atomic mass of one atom of oxygen. So for dioxygen, it is 16 times 2, that is 32. Then we have the temperature. Temperature of XO2 is 327 degrees Celsius. So uh, 327 plus 273, that we have to add up. So it will be some 600 kelvins divided by molar mass of XO2. So let's say molar mass of X is X only and molar mass of oxygen we know as 32. So these two RMS speeds are going to be equal as per the question. So we have to figure out what is the uh, molar mass of X. So like now let's basically evaluate them. So this would be 1 upon 32 is equal to 2 upon X plus 32. So this implies the value of X will be some 32. So that means our atom which we are looking for would be sulfur. Sulfur has the uh, sulfur has the atomic mass of 32. Oxygen has an atomic mass of 60. So sulfur has twice of that. So here you can see that two factors also coming in play. So this is one of the JEE mains questions. Then we have question about average kinetic energy. So average kinetic energy of a monatomic molecule is simply 3 by 2 kT, or the average translational kinetic energy. Average translational kinetic energy of a molecule at T temperature is equal to 3 upon 2 kT. So here we know that this is for one single molecule. Um, Now, since a monatomic molecule only has translational kinetic energy, so this becomes the total kinetic energy of a monatomic molecule as well. Mainly, if we have a diatomic molecule, uh, the translational kinetic energy, sorry, the translational kinetic energy, it remains the same value, that is 3 by 2 kT. The total internal energy of the gas, if it is diatomic or triatomic, is the degree of freedom times kT by 2. So that means that it has more total internal energy uh, per mole of gas at T temperature than in comparison to a monatomic gas. So we have a case here. So in the last lecture, basically, I want to discuss one point. In the last lecture, I discussed what is the total internal energy of a gas. So there I said that the total energy of internal energy of a gas is 3 by 2 RT for 1 mole of gas. So that is a statement for a monatomic gas. In general, we encounter monatomic gas only. So usually that is the total internal energy for that gas. But it is actually the total translational kinetic energy for a gas. Then we have estimate the average thermal kinetic energy of a helium atom at room temperature, that is 27 degrees Celsius, at temperature on the surface of sun. So temperature at surface of sun, what you would imagine? It's 6,000 kelvins, pretty high. Then temperature, there was one more option, or temperature of uh, nuclear fusion. So nuclear fusion is basically 10 to the power 6 kelvins. Um, so using this formula, I can figure out what is the average kinetic energy of a helium molecule at this particular temperature. So let's figure out. So first option would be 3 by 2 Boltzmann's constant. minus 30 minus 23 into temperature 300. So this value, after calculation, we can figure out what will this value be. So this is up to 0.69. Um, so times 9. So 69 times 9. That is 99, 81, 96, 54. So this is 621. So this is 6.21 into 10 ki power uh, minus 21 joules. Yes. Similarly, if I multiply this 3 by 2 kT with sun's temperature, so its value would be some 1.24 into 10 to the power minus 19 joules. Then we have uh, basically questions on molar heat capacity of a gas. So let's move in that direction as well. Molar specific heats of a gas. So we have two molar specific heats of a gas. First is molar specific heat at constant pressure. So this is heat supplied to the system to raise its temperature by 1 Kelvin per unit mole of gas at constant pressure. So this is given by capital C and P, molar specific heat of a gas. Its value for our purpose is 1 plus F by 2 into universal gas constant. So this might be, I think, not visible because of the brightness. So I'll write this again. So this is Cp is equal to 1 plus F by 2 into universal gas constant. So we know what is universal gas constant. What we want to know is what is F. So F is degrees of freedom. Degrees of freedom means that in which directions the gas can acquire energy. So although energy does not has any direction per se, right? Degree of freedom I'm speaking. So when a gas starts moving, it has velocities in x, y, and z direction. So it will have kinetic energy half mvx squared plus half mvy squared and half mvz squared. So immediately you would have remembered. Okay, we just learned in the last class that uh, average uh, distribution of velocities in x direction, in y direction, and in z direction is calculated using those values only, vx squared, vy squared, and vz squared. If we add them up for each particle and take an average, they should be equal. So this means that the kinetic energy of a gas is basically distributed equally in these three modes, or these three directions, that is x, y, and z. So these directions we don't say kinetic energy can have a direction. So we say mode. Direction kinetic energy is distributed in x, y, and z. These modes. So these are for a what we say monatomic gas, because it can only translate. If we have a diatomic gas, then it can also rotate as well. So we then have two additional degrees of freedom. So this value F is 3 for monoatomic gas and 5 for a diatomic gas. For a triatomic gas, it is 6 and so on. So these are the values. Then we have the molar specific heat of gas at constant volume. Um, for a constant volume, when we supply heat, the heat supplied is gone entirely into increasing the kinetic energy of the gas. There, we see the definition is heat provided to the gas per unit mole per unit rise in temperature at constant volume. So this is CV. Its value is F by 2 into. So we also have a relation that Cp minus Cv is equal to R. So this is Mayer's law or Mayer's relation. So for today, only this much. Thank you.